Okay, hello everyone. Happy Friday. Another week flown by. Here we are. So you had your web work due last night, and then the next web work is posted. I think it's either due Monday or Tuesday night. That's the spherical triple integrals homework. So get going on that. Also, I just posted some preparation resources for Wednesday's exam. We're gonna have the exam on Wednesday. Definitely want to get going on that this weekend. Think about carving out lots of different times between now and then to study. Don't start studying Monday night or Tuesday. So there's a process of working at it, letting it settle for a while, working at it some more, and then you need that time before the exam to get questions answered. So that process can't happen in 24 hours. So make sure you start studying for that exam this weekend. Um, it will cover everything, so starting with double integrals all the way through what we do today, which is something totally new, but just a little bit of the exam, a couple questions might pertain to what we do today. And there might also be a short web work on today's stuff, not a full web work, a short web work on today's stuff that would pertain to the exam as well. Also, with the prep materials, I will post another extra credit written assignment today. So everything will be updated this afternoon in terms of everything you need for homework and the exam for Wednesday. Any questions before we start? Alrighty, so I want to talk about. So we finished up cylindrical coordinates, spherical coordinates, and triple integrals. You've got your triple integrals homework for spherical due early next week. So we want to change gears here in the course and look at. I gotta share my screen with you. So as we work our way through this course, what happens is that we see a lot of different kinds of functions that we're dealing with. So I think it's important to take a second to kind of organize all the different kinds of functions that we'll see and kind of summarize them all together, so we have a structure in our brain, a kind of filing system of these different functions, rather than just kind of learning these things and not really seeing that, hey, we're learning about all these different kinds of functions. So let's take a few minutes to summarize those. So for each kind of function, we're going to talk about its conventional algebraic form. For instance, like what kind of formula do you typically see for these? And then how it graphs and in what coordinate system. So here we go. This first type is single variable real valued function. So one of these two things pertains to the independent quantity in the function, and one pertains to the dependent quantity. So if independent and all functions have something going in, and the function then gives you something back, right? So the independent quantity is what goes in, and would that be our single variable or our real value? So the single variable, is that talking about the independent thing or the dependent thing? Yep. How many variables you have of a function would be independent? That would be like, so we have one variable, and then the real value is what the function gives, right? So that's the dependent quantity. So this first type of function, you have a single variable, and then the function takes that value and returns a corresponding real value. And so what would be our typical algebraic form for that? So these are the functions you've been dealing with for most of your algebra and calculus career. So what are those typically, like what's our conventional kind of algebraic formula for that?
Y equals mx plus b.
Well, that would be if it was a line, But if it were any function, yeah, so you got the, yeah, just like, so we like the typical kind of convention is to say f of x, right? So y, the real value, is a function of x, the independent variable. So y is some function of x, which is our single variable that this function acts on, right? So it takes a value of a single variable, and for every one of those returns a corresponding real value, which is y. So how do we graph those? Where and how do we graph those?
R2.
Yep, those graph in the plane. And so how do these graph? Like as a point, as a string of points, as a region? What do these typically graph as?
A curve.
Yeah, like a string of points, right? So it could be like a curve, or that curve could be straight and be a line. And so then we know that given any x value, say x1, the function gives us a corresponding y value, say y1, and then we plot all those points. For varying x, we plot the xy ordered pairs, and that'll give like some kind of string of points in the xy plane. Okay, so like I said, this is what you've been living most of your calculus career, dealing with these kinds of functions. Okay, what about a multivariable real valued function? Have we seen these before?
Yes.
So multivariable still refers to the independent. So we have more than one independent variable, and the function spits out a real value. So what was the general form of these that we saw?
F of xy.
F of xy, right? And the convention for the value, that real value was?
Z.
Good. So we said z equals f of xy. Now we also saw a 3-variable real valued function. When did we see that? Remember when we saw those?
While we were doing triple integral.
Yeah, good. So we didn't spend a lot of time, but we said that when you do a triple integral, if you were to integrate something, that could be a 3-variable function. But we spent most of the time, like the last month, working on these. How and where do these graph? How and where do these graph z equals a function of x and y?
In R3 is like a curve.
Okay, a curve in
Or
R3.
surface.
Agree with that?
I'd say a surface.
Oh, you changed your mind. A surface, okay. So is it a curve, a surface, or a solid? Z equals a function of x and y.
Surface.
Surface, right? So for every xy ordered pair in the xy plane, right, you get a single z value for every x and y. And this made like a surface. Let me do that. There we go. Surface in R3, right? So for every xy ordered pair, that would be like the whole xy plane, there's a corresponding z value. You put all those points together, they'd form a surface. And that's what we said, right? We said single equation of x, y, and z is a surface. That's like our sphere, our plane, paraboloid, cone, cylinders, right? Single equation of x, y, and z makes a surface. But there was another way that we were able to graph these actually in R2. Do you remember what that was? We could actually represent these in R2.
In
Someone said it.
contour plots.
A contour plot, right? A contour plot. So these level curves gave values of constant z, and they were, at those locations, x, y locations. So you still have x and y as the independent thing, and then the level curves tell you what value of z you had. So it was a two-dimensional way to reveal this, to show or represent the three-dimensional surface using level curves and a contour plot. Okay, so those are our multivariables. So you have more than one input variable taken in combination, and the function then takes those and gives you a corresponding real value. And that was like, these are like the ones that we integrated for triple integrals, right? We said these were like 4-dimensional surfaces or hypersurfaces. Okay, what about a single variable vector valued function? Do we see these? Single variable vector valued function. Do we see these? Have we worked on these?
Parametric.
Okay, so a vector valued function is very similar to parametric equations. So yeah, vector functions, right? Vector functions, we did vector functions where t was commonly what we called the variable or the parameter. And then given every value of t, so this was like our position function, right, in space, like an object flying through space or in the plane. And for every value of t, which could be time, we get a vector that gives us like a position vector. And then we saw the derivative, vector derivative function was the velocity. Second derivative was acceleration, which had 2 components, right? It had the tangential component and the normal component. So we spent a week or 2 weeks on vector functions. And so how does this particular vector function graph? First of all, R2 or R3?
3 or 2.
This one will graph in R2 as what? As a point, as a vector, as a curve, as a region.
As a line with the line starting from the origin to whatever point is specified by x and y.
Okay, so that would be an individual. Yes. So each value of t gives us a vector, and so then we could plot every one of those vectors in standard position with its tail at the origin, and let t change, and then what would it give us?
A curve.
That gives us a curve, right? So this was like the laser show, right? The vectors in standard position that come out of this function give us a curve. This would be in the plane, and then if it were an R3 vector, that would be a curve in space, right? So we spent 2 weeks on these, right? Multivariable functions of 2 variables give surfaces in space. Vector functions that give 3-dimensional vectors give a curve in space. So surfaces in space, equation of x, y, and z, or a multivariable function. Vector functions of 1 variable gave us a curve in space. All right, finally, what about a multivariable vector valued function? Have we seen these? So what does this mean? It means that we've got more than one input variable, and that combination of values is going to, the function will give us a vector. Have we seen these before?
No.
The answer is no. We have not seen these. So now we have more than one variable. The function processes a combination of values and spits out a vector. And now notice each component of the vector is a multivariable real valued function, right? It's taking 2 values and spitting back 1 to be that component of the vector. So we have 2 multivariable real valued functions that are the components, put them together, it makes a vector. So we could have an R3 version of this too. So this is what we're going to work on today, what we haven't done yet. Multivariable vector valued functions. Okay, so let's do that. Questions on this kind of survey of the different functions? So these you've seen these. Oops, you've seen these forever, and we worked on these 2 up until this point in the course. We've been working hard on these 2 types of functions: multivariable real value, vector value functions. Was there a question?
Can we compare to the RT with 3 vector volume what it looks like in the R3?
This one?
Yeah, no,
Yeah.
the last section.
Yeah, what will this be in R3? Every value of t gives a vector. Put the vectors in standard position and let t increase. What will you get?
It's like a curve, and maybe.
Yeah, right. It's a like think of it as like position curve, right? Vector, single variable vector valued functions give curves. We worked hard on that. So if it's the R2 vector function, it gives a curve in R2. If it's an R3 vector function, it gives a curve in R3. We put all the vectors in standard position, let t increase. The tips of those vectors sweep out a curve. Okay, but today we're going to work on multivariable vector valued functions. We're going to introduce those. So, all right, so here is how this works. We've got, this is my x value. This is my y value. So these are the independent variables, x and y. So that's what goes into the function. And then we're going to get some kind of vector out. And so there is a particular function that we're going to look at here. We're going to look at a kind of one location or one coordinate pair and vector at a time. So right now I'm showing that x is 2 and y is 1. And what is that? That's location. That's this location in the plane. And so for x equals 2 and y equals 1, what vector do we get? So this is the vector that we get. So what's the x component of the vector?
1,
1. What's the y component of the vector?
2, -2.
-2, right? Components of the vectors give the variation in those components, right? In those variables. So the x component gives the variation in x. How much does x vary? It varies by 1, positive 1. Or 1i. And then the y component of the vector gives the y variation. How much does y vary? -2j. So this is the vector 1, -2. Oops, put it in the wrong place. So some function that we don't know about, we know one thing about it now, that if you put in x equals 2 and y equals 1, meaning this location, you get this vector, 1, -2. Okay. Let's look at, how about x equals 0 and y equals -2. So here's the point, 0, -2. So that's this point, right? So the independent thing, the multivariable part of this is the location in the plane, 0, -2, and at that location, the function assigns a vector. What vector did it assign?
-2, 0.
-2, 0. Okay, let's do another one. Stop me if I lose you. So how about, let's do x equals -1 and y equals +2. So here's the point. So the input or the independent thing is a pair of x and y, which is a location. So location is -1, 2, And what vector does this function give?
2, 1.
2, 1.
So, Professor, are you, the way that I'm kind of getting it is, are you basically just kind of inverting the points and then assigning the opposite sign value for the y?
Well, so that's what we're trying to figure out. We're saying this is a particular vector function, and it's so that the components, the x and y components, come from some kind of system based on what x and y are. So yeah, so you're figuring it out. That's right. All right, let's do another one. So how about y equals 0 and x equals positive 1. So here's the point 1, 0. At the point 1, 0, what vector do we get at 1, 0?
0, -1.
You want 0, -1. Okay, so we're trying to figure out this particular function. So what does it look like the x component of all these vectors is based on x and or y?
-y.
He wants that x is -y. Agree with that?
It's just y.
Just y, right? It looks like the x component of our vector is always the y coordinate of the point. 1, 1, -2. Okay. What about the y component of these vectors?
Negative x.
Negative.
Yeah, it's the opposite of x. So this is our multivariable vector function here that we were working out. And what does it do? So this particular function, to get the x component of the vector, you take the y coordinate of the point. And to get the y component of the vector, you take the opposite of the x component, or the opposite of the x coordinate. So then what we have here is if I would show you lots of those vectors at once, it would look like this. Okay? And so what's the idea? The main idea is every location, this function assigns every location a vector. This function assigns every location, x and y, a vector, so that, and the vector that you get for this function is the x component is the y coordinate, and the y component is the opposite of the x coordinate. So then what you get is this thing that looks like a giant clockwise kind of whirlpool. What if I were to show you every vector in this vector field? What would it look like if I showed you every vector?
Circle.
So for every location, there's a vector. Here I'm only showing them on at the whole number values of the coordinates x and y. What if I were to show every vector at every location? What would you see?
Circle.
Concentric circles.
That concert clock.
Lots of blue.
So the last person, what'd you say?
Said lots of blue.
Lots of blue.
The whole thing.
This is what you'd see. This is what you'd see if I showed you every single vector, because every single point in the plane would have a vector associated with it. And so this is what you see. You just see blue. So in order to represent a vector field, we just show some of them. We just show, like, for instance, this is showing them at every whole value of x and y. And on top of that, it's actually not showing the magnitudes correctly, right? So it's showing, so if, what do we say? At 2, 1, 2, 1, what was the vector? 1, -2. Oh yeah, like this. So what is actually 1, negative 2 is this vector right here. So notice that it's showing it much, much, much smaller. It's barely, you know, it's like this long, like that. That's because if they showed all the vectors with it were actual magnitudes, they would all be crossing each other. It'd be very difficult to see. So a common way to depict these is, you know, reduce the magnitude greatly, but then keep the relative size the same. The relative size of the vectors to each other the same. So this for this particular vector function, the further you move away from the origin, the bigger the vectors get, and so you can see that effect. But the sizes are all shrunk down so that they don't cross and make a mess.
Are they divided by the same amount?
Yes, right. So it's
Okay.
proportional. So that the relative size is the same. The relative sizes are the same, but all the sizes are scaled down by a certain amount.
And because the vector is, related to the coordinates, of course, it would make sense that as you increase, the coordinates and you get further away from the origin, the magnitude is going to be bigger.
For this function.
Yeah.
For this
one.
particular function,
Yeah.
right? This is just one of
Yeah.
of a gazillion functions you could create like this.
Yeah, there could be, infinite technically.
Okay, so every location, here's the key. Every location has a vector associated with it. That's what these functions do. Multivariable vector valued functions are, they assign a vector to every location, right? Your location is your multivariable, either xy or it could be xyz, and then you get a vector for every location. So this is what's called a vector field, a field of vectors. These functions are called vector fields. All right, so let's do another one of these for practice. I'll do a more challenging one. So questions on the basic?
Yeah, I have one. Are these like the fields we see in, say, differential equations that model the long-term behavior of the solution of said differential equations? Kind of.
Maybe there might be differential equations that could be represented by a vector field. That's possible. Yep. I don't remember that specifically, but that's very possible. Okay, let's look at another one here. Another one. All right, so here's a new one. We'll just start with this point right here. We'll figure this out. Okay, so this is, again, this is still x and this is still y. So now we're starting with our location over here. That's our input variable or input thing, two variables. So 1, 0 gives what? A vector. What does 1, 0 give? What vector does that give?
2, 1.
2, 1, right? So at the position, at the location 1, 0, we get the vector 2, 1. Okay, let's change it up. Just rapid fire here. How about negative 1, negative 2? What vector do we get at the point negative 1, negative 2?
Negative 1, negative 1.
Negative 1, negative 1. Okay.
Isn't that point negative 2, negative 1?
Yeah, something's wrong here. Yeah. I don't know why. I've done that in the other class too. I always reverse these. There's something about the way this is up here that I keep reversing this. This is negative 2, negative 1. Okay. And then let's do, how about 0 for x and positive 2 for y. So here's point 0, 2, and the vector we get at 0, 2 is?
1, negative 2.
1, negative 2, okay. So after we get 4 or 5 of these, we start looking for a pattern. So how about -1 and +1? So here's the point, -1, +1. That's right here. What vector do we get for that?
0, -2.
The -2.
0, -2. Let's do one more. How about +2 for x? And, oh, I don't know, -2 for y. So we're at the point 2, -2, right there, and the vector that I get is?
Three-fourths.
Looks like 3, 4. Okay, so this one's just slightly more. So the x component could be a function of x and or y. It could be just x, just y. It could be a constant, or it could be a function of both variables. So anyone see the pattern for the x component?
X plus 1.
Someone's offering up x plus 1. Does it work? 1 gives 2, -2 gives -1, 0, 1, -1, 0. Looks like it works. So here the x component of our vector is 1 more than the x coordinate of the location. What about the y components of these vectors?
X minus y.
Someone is saying x minus y. So x minus y would be 1, -1, -2, -2 again. Looks like that works for all these. Okay, so here is another vector field. It's the function. Takes location, gives back a vector according to x coordinate plus 1, and then the x coordinate minus the y coordinate to get your vector. Let's take a look at the whole field. The whole field looks like this. This is the idea of this field here. And again, these vectors are they're not the right lengths. They're much shorter than the actual lengths, but relative to each other, they're the right size. And then what you see then is if this were, say, common examples of vector fields are like a wind flow or fluid flow. So maybe this is a channel of water, and this is how the water is flowing in terms of direction. At any point, there's a direction and speed of flow. And so what you see then is if you drop something into this field, you could trace where it goes, how it moves according to the vectors, and that would be creating what's called flow lines. Maybe if there's a flow line, something like that. And so you could make lots of these. Doing my best, so something like that. So the flow lines for this vector field is kind of like if you were to drop an object into the field and watch it move, the path along which it would move would be the flow lines. It's kind of like connecting the vectors together to see the overall flow of the field. Okay, so does the basic premise of a vector field make sense? It's a function of, you get vectors as a function of location, right? Every location has a vector. And the vector is determined by the coordinates. So these could be functions of x and or y. So just show you a couple examples, real world examples here. So here is, this is actually showing the vector, it's like the vectors and the flow lines. So because they're curved, it's really showing the flow lines and not the, like vectors, you don't draw them curved, right? You draw them straight. So this is showing the flow lines for, so like 3-point charges, two positive charges red, one negative charge black. And so when they're positioned such as they are, you get a electromagnetic field. So it's kind of like if you were to drop an electron into this, and it would hit a flow line, it would move along that flow line. So everything close to this positive charge, everything negative gets sucked into it, right? Here it's more complicated because you got a positive and a negative almost right on top of each other. So you have repulsion from the negative charge, the black one, and then attraction to the red charge. So you see how something gets repulsed off and then gets kind of pulled back around on the other side to the positive red charge. So like a wind field. So here's like a wind field of the northern hemisphere, North America, and notice Arizona. Typical day in Arizona, hot and no breeze, right? So the vectors have basically a zero value, meaning there's no wind velocity. Other places showing the magnitude of the vector is the magnitude of the flow there, and then the direction, of course, is the direction of flow. Here's the Gulf Stream around Gulf of Mexico and the Atlantic Ocean around Florida. The white is then showing you flow lines around the tip of Florida. Okay, so magnitude vectors give magnitude and direction. So if it's the Gulf Stream, then you have higher velocity flow through here in this direction, and where you have shorter vectors, you have lower velocity flow.
Are the colors also like relevant to this example, or
I don't know.
something else?
I don't know why they've colored the water the way they did. It doesn't look like the color is indicative of the magnitude of the vectors because you have if you look at the largest vectors everywhere, it's all the colors. You got orange and yellow and blue, green. So I don't really know what the colors.
It looks more like temperature than anything. Because if you look,
yeah, that's true.
up
Yeah,
north,
as you go up, you get cooler. So it's kind of the temperatures. The color is showing something different, right? It's showing temperature, whereas the vectors are showing the vector field for like the Gulf Stream. Okay, so I have an exercise here for practice. So I have these. Not that one anymore. I have 4 vector fields that we're going to figure out what they are by looking at them. Instead of one vector at a time, we're going to look at just the big picture of it and see if we can figure out what the vector field is. Now, the components can only be, to make this actually doable, the components are only allowed to be, where should I write it? Up here. So the possible components are plus or minus x, plus or minus y, plus or minus 1, and 0. Okay, so the x and or y components can only be one of these 7 things. Plus or minus x, plus or minus y, plus or minus 1, or 0. Okay, so let's start with this one here. So we're looking at the vectors in the field, and we're trying to figure out what is the x components of the vectors and what is the y components of the vectors. So for this one, maybe we'll start with the y components of the vectors in the field. Maybe that's the good place to start. So what are the y components of these vectors?
0.
There's 0 for all of them, right? So that's perfectly legitimate. component in a vector field is that no matter what vector you're looking at, its y component is 0. Okay. Now, what about the x components? So one thing you can look at is, as you move in the x direction or as you move in the y direction, how does the components change? So like we can come here and we can move in the x direction and say what's happening to the x components of those vectors. We can move in the y direction and say what's happening to the x components of those vectors to kind of try to help us figure out what is the x component. So do the x components change when we move horizontally, or do they change when we move vertically?
Horizontally.
Just horizontal.
Horizontally, right? So that means that this component is going to be a function. It looks like it's just going to be a function of x only, and not y, because if you move in the y direction, it doesn't change. If you move in the x direction, the x component changes.
It
So
looks
here-
like it would be linear to me, the way that the vector is changing in
Okay,
that
it can
direction.
it can only be any of these. So it can't be quadratic or anything else besides these.
Oh, okay.
So those are the only possible ones. So as we move in the positive x direction, what's happening to the x component of the vectors?
They are going to 0.
I suppose it's decreasing since it's pointing towards negative x.
Okay, so they're getting bigger in magnitude, but are the x components positive or negative?
Or negative.
Negative, so they get more negative, right? So as we increase positive in the positive x territory, the x components are negative and getting more negative. And then similarly, if we go in the negative x territory, what happens to the vectors? They get more positive. So what does this have to be?
Negative x.
Negative x. So if your x coordinate is positive, you get a negative x component in your vector, and those components get bigger negative, the bigger positive your x coordinate gets. Similarly over here, the x components are positive when the x coordinate is negative, and as your x coordinate gets more negative, your components get more positive. So that's exactly what negative x is. Questions on this first one? Does it make sense?
Yeah, Professor. So, if because I brought this up with respect to differential equations, would then I guess 0 here kind of by the direction that the vectors are going to, would then in this case in the upper left-hand corner, would the equilibrium solution be say 0, and then you'd have stable solutions for say the lower left-hand corner. instead of the upper
Maybe.
left-hand.
It's been a while since I took differential equations, so you may be right. You may be onto something there, but I don't remember that specifically. Okay, so let's go on to this one here. So this one a little more complicated. We got both an x and a y component. So let's start with the x components. So what are the x components of these vectors? So let's draw them out here. Do they seem to be changed, the x components, do they seem to be changing as the x coordinate changes, or as the y coordinate changes, the x components?
It looks like it's just the y that's changing. Yeah,
We're
it's
talking
in this
about the
case.
x components of the vectors, the horizontal components. Do they change when you go up and down, or do they change when you go horizontally?
Equal horizontal.
Only up and down.
Only when you go up and down, right? When you go horizontally, the x components of the vectors, here's an example, the x components of the vectors are staying the same. See that? But when you go up and down, the x component changes. So that means the x component is a function of which, y or x?
Y.
Y, right? So as you change y, the y coordinate, the x component of the vector changes. And look, so going up, we're getting more positive. The x, as the y coordinate increases, the x components get bigger. And as the y component decreases in negative territory, or coordinate, the x component gets bigger and bigger negative. So what is the x component of these vectors?
Y.
Y.
Positive Y.
Positive y. Okay, let's look at the y components of these. So how do the y components change? Do they change as x changes or do they change as y changes? Let's look. So here's these y components. Changing my x coordinate. Do the y components change?
No.
No. Changing my y component coordinate. Do the y components change?
Yes.
Yes.
Yes. And look, so the y component is also a function of y. It also changes as the y coordinate changes. How does it change? So the y components in positive y territory are
Negative Y.
getting more negative. And the y components in negative y territory get more positive. Therefore,
Negative Y.
negative y. All right, did I lose you? Does it make sense?
I still don't get how you give a y as an x vector.
Because the x component of these vectors does not change as x changes. It's not a function of x. Do you see that? If I move in the x direction, I get the same x component every time. But if I move in the y direction, then my x component changes. So my x component of these vectors is the y coordinate, right? The y coordinate's increasing positively. Well, so are my x components of my vectors increasing as I go on the increase y. But if I change x, the x components of the vectors stay the same. They're not a function of x.
Thank you.
Let's do this one here. Last one. X components. What about the x components of these vectors? Do they change in the x direction? Do they change in the y direction?
Y.
Direction.
They look constant.
They're the same everywhere in this field. Do you see? I'm drawing the same little component for every vector in this field.
So does that mean that it's 1? Or I mean, technically,
It has to be one of these.
oh,
So what does that have to be?
it has to be 1.
Positive 1.
Yeah, positive 1.
All the x components of these vectors are the same and they point to the right, a constant amount. Your only
And
choice
that
there
would
is positive
explain-
1.
And
What-
that would explain why it kind of,
What about the y?
kind of looks like a parabola.
What about
if you were to,
what about the y coordinate components?
Maybe x.
They stay the same in the y direction, but look, they're increasing in the x direction. The y components, as x increases, they get more positive. And as x decreases negative, gets more negative, the y components get more negative. Therefore, y component is x.
I said x, but I'm not sure it's correct.
Yeah, you were right. It's x. Because as x increases, your y component increases. They're the same. As x gets more negative, the y components get more negative. But if you move in the y direction, the y components stay the same. So it's not a function of y. This component is a function of x.